We're going to talk about the electron configuration of the transition metals. The electron configuration is the arrangement of electrons in an atom's orbitals, and the electrons are arranged in the most energy efficient order. And this diagram is the Aufbau principle, which gives us that specific energy efficient order. So we're going to fill up the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, so on and so on. We also have to remember that the S subshell can hold a maximum of 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold a maximum of 10 electrons, and the F subshell can hold a maximum of 14 electrons. Now, the transition metals can be tricky because there are exceptions to these rules. So let's start off with the first example, iron. Let's determine the electron configuration of iron. We have to find iron on the periodic table. Iron is right there. So the atomic number for iron is 26. So that means that iron has 26 protons. This is a neutral iron. So neutral iron will have 26 electrons. So we want to figure out the electron configuration of 26 electrons. So we're going to follow the principle, and we're going to fill up the shells in that order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. If I add up all of the superscripts, 2 plus 2 plus 6 is 10, 12, 18, 20, 26. That gives me all of the 26 electrons. Now I want to talk about the noble gas configuration or the abbreviated electron configuration. We still look for the previous noble gas. So iron is 26. The noble gas before that one is argon. Argon is 18 electrons, so that means we're going to account for 18 electrons. So my noble gas abbreviation or my abbreviated electron configuration is we're going to put argon in brackets. That means 18 electrons, and what's left over is the 4s2, the 3d6. Now, when it comes to the valence electrons of transition metals, the valence electrons are going to be the electrons in the outermost shell. And for transition metals, it's easier to see the outermost shell when we have the abbreviated electron configuration. So 18 electrons are for the first electrons, and the outermost shell will be these 8. So iron has 8 valence electrons. Different than what we do with the main group elements. So we have the electron configuration, the expanded electron configuration. We can determine the abbreviated electron configuration. We can also do the electron configuration for ions. Now, if iron were to have a 2+ charge, that means it would behave as a cation, and cations give away their electrons. So iron 2+ just means it will give away 2 electrons. So a neutral iron will have 26 electrons. A cation 2+, that would just mean 24 electrons. And we look for the highest quantum number, the highest energy shell, and we're going to take away those 2 electrons. So the highest quantum number is 4. So we're going to take away those 2 electrons first. So Fe2+ is 1s2, 2s2, 2p6, 3s2, 3p6. We're going to take away those 2 electrons and end up with 3d6. This is the electron configuration for iron 2+. Let's talk about another example. let's go ahead and talk about the electron configuration of copper. Now, I mentioned earlier that there are exceptions to the rule, and the exception for transition metals is that they prefer to have a half-filled or a completely filled D subshell because that's more stable. And there are a few of these exceptions. Copper happens to be one of that, but if you don't necessarily remember, we can actually see that setup in our electron configuration. So let's take a look at copper on the periodic table. Copper, a neutral copper, will have 29 electrons. So let's go ahead and write down the electron configuration for copper. We would expect it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. This is what we would expect it to be. Let's examine that. We know that transition metals prefer to have a half-filled, or completely filled D subshell. So D can hold 10 electrons. It would prefer to have 5 or 10. I see here that the 3d9 is not completely filled, but I can go ahead and take one electron from here and make that 3D into 3D10. So what we would expect it to be is not the correct one, and we're going to fix that. 1s2, 2s2, 2p6, 3s2, 3p6. We're going to take one of the electrons from the 4s and move it to the 3d. This is the actual electron configuration for copper. We can also do the abbreviated electron configuration. We still use the same rules. We go to the previous noble gas. So here's copper. The previous noble gas is argon, and argon is 18 electrons. So we're going to take into consideration these electrons. We're going to put argon in brackets and go ahead and write down the rest of the electrons. We can also do the electron configuration of charged particles. So if we wanted to do the electron configuration of copper 2+, 2+ means that it loses 2 electrons. If a neutral copper has 29 electrons and it gives up 2 electrons, then it would have 27 electrons. So we're going to give up. We always start off with the highest quantum number, the highest energy shell. And our electron configuration for the copper 2+ would be 1s2, 2s2, 2p6, 3s2, 3p6. I'm going to give up 1 electron from the 4s and 1 electron from the D, the 3D. So now it becomes 3d9. So for the transition metals, there is an exception to the filling up order. And most of the exceptions are going to be, or the more common ones is going to be chromium and copper. But there are other exceptions for the transition metals. Good luck and keep practicing.